Hello everyone, my name is Julius Pisecki and I'm the manager for data and computing here at Leap. Today I would like to talk to you about our cloud-based data and computing platform Leap Pangeo, which supports our research, education and knowledge transfer within Leap. The key components of our infrastructure are our data library, which combines both public datasets as well as datasets produced within Leap, all located within Cloud Object Store. We pair this computing resources with pre-configured environments. This enables us to provide both quick access to compute for data exploration, as well as scalable distributed computation for large analysis jobs. These components are accessible via a Jupyter Hub, which is maintained by 2i2c, a nonprofit organization that manages cloud infrastructure for research and education communities. A Jupyter Hub manages cloud resources to serve computational notebooks to a community of many users. To access these resources, registered Leap members require nothing else but a web browser. Just open a website, choose from several options for software environments, CPU and RAM configurations, optionally this includes GPUs, and then click Start. After a short spin-up time, your personal server is ready and you're greeted by the Jupyter Lab interface. The Jupyter Lab interface is a web-based interactive development environment primarily for computational notebooks, used by researchers, students, and data analysts around the world. The interface provides you with a terminal similar to what you have on any Unix machine, or for instance, your MacBook. If you prefer this workflow, you can navigate the file system and interact with, for instance, Git directly from this terminal, as you would on your local computer. But there's also an interactive file browser where you can navigate the file system, inspect the repository I just downloaded, and open and edit, for instance, text files. But most importantly, you can run Python code in interactive Jupyter notebooks, but more on that later. Our primary motivation is to support ambitious research objectives. We believe that by enabling seamless collaboration with high-performance computing and analysis-ready data, we can truly accelerate research progress. These advantages directly translate to events like the Train the Trainer Bootcamp, a 2-day workshop, which was a great success and very fun to run. The multidisciplinary research and learning community consisted of students, researchers, and data scientists and engineers from various businesses. Participants were able to seamlessly follow along with exercises about efficient and fast analysis of climate data and how to use machine learning with climate data. The infrastructure also supports rich data-driven classroom experience for learners, eliminating the need for expensive equipment and helping them transition successfully from coursework to research. We aim for education and research to be a bidirectional experience where the latest research techniques are taught in class and learners are empowered to apply and improve upon them when they transition to research. Now let me demonstrate how you might go about exploring some data within the Leap infrastructure. As Kata demonstrated in the session this morning, we can take some of these datasets, in this case a precipitation dataset from CMIP6, and continue our exploration after we've sort of looked at the maps in a Jupyter notebook. And here we have all of the capabilities to compute new maps, zoom in on areas that interest us, or compute more difficult or much more difficult metrics, combining several datasets. In this case, what you're seeing here is just a map of precipitation differences between the beginning and the end of the century for the upstate New York area. But in this environment, I just wanted to demonstrate how you can go seamlessly from looking and exploring at a data set very rapidly in the Carbon Plan data viewer, and from there go seamlessly into a computational environment and extend your analysis and customize it to your use case. If there's one aspect I would like to highlight in particular during this event, it is the curation and co-maintenance of large open access climate datasets. Many of these datasets present immense value for a variety of different stakeholders, but understanding, cleaning, and converting datasets to analysis-ready cloud-optimized formats is hard work. If every research lab, company, nonprofit, etc., takes on this task by themselves, this will result in high costs, duplicated efforts, potentially undiscovered bugs, and maybe most importantly, everyone who is not part of these organizations is effectively banned from engaging with this data. An alternative to this is a tighter collaboration between stakeholder groups, resulting in high quality public data sets that enables more equitable use of the data for all kinds of science application, informing policies, and deriving for-profit data products. A prime example of such a dataset is the Coupled Model Intercomparison Project, short CMIP. CMIP is a global coordinated effort to run many different simulations of the Earth based on different climate models from many modeling centers around the world. Each center runs their climate model with prescribed external forcing scenarios. The scenarios describe several possible cases of human behavior, including greenhouse gas emissions, land use, and others. And they represent, for instance, business as usual, a strong mitigation scenario, or a middle-of-the-road trajectory. The resulting petabytes of data are distributed via federated efforts of participating modeling centers in the Earth System Grid Federation, and can be used to predict future changes in the climate and quantify the uncertainty of these projections. In fact, most of this data presents the basis for the Intergovernmental Panel on Climate Change and its reports, and is also increasingly used in the private sector. But working with this data is notoriously hard. The common workflow involves downloading subsets of the data, and then oftentimes additional cleaning and pre-processing is needed to work with the data. In the past years, the Pangeo project has converted and uploaded a large part of the full archive from NetCDFs to analysis-ready cloud-optimized ZAR stores. Partnering with cloud providers, the data is hosted as part of the Google Public Datasets program and also freely available on Amazon S3 cloud storage. Combining this public data in the cloud with open source software developed and used within the Pangeo community enables you to reproduce scientific results from the Intergovernmental Panel on Climate Change report in just minutes from the raw data. And I'm going to demonstrate that right now. In this demonstration, we're going to look at some CMIP6 data. We're going to choose only a few of the models. And the first part of this exercise is basically subselecting several of the simulations that are tagged as, for instance, the historical, under known forcing, and some of these SSP scenarios that I mentioned before, which represent either a very ambitious and optimistic scenario, middle of the road, or business as usual. We end up with a lot of lazily loaded X-ray data sets. We also need to include the cell area here to compute correct averaged sea surface temperature. That's what we're looking at here. And just as a little nice addition that just came out of the open source community, this is the data tree object that basically gives you a collection of many X-ray data sets that are organized in a tree-like structure. This makes analysis very easy. We're working with about 20 gigabytes of data here. So since we're working with sea surface temperature, this is not that much data. But you can do this with the full 3D data just as well. So what we're seeing here is now one average sea surface temperature from a single model. And what we're doing to finalize this plot is remove an anomaly from the 1950 to 1980 period. And then we can plot the data. And it looks remarkably similar to the plot of the IPCC report. And that was done in a very short time. And you can see that this is all possible based on raw data in the cloud in a very short amount of time. Something like this would have not been possible without the collaborative open source development and the data in the cloud. I think this is a really powerful demonstration how the combination of analysis-ready data, scalable compute, and community-driven software can accelerate science and enable more people to work with big climate data, and thus really make science agile by having the ability to improve on hypotheses, rerunning analyses, and really sort of optimize the outcome and really truly understand what's going on in the climate system. As I mentioned before, this also enables many more stakeholders to reproduce and build on scientific results. In the end, I think there cannot be enough hands on deck, enough stakeholders looking at the same data and sharing efforts to work together rather than in parallel. To me, this is the only way to drive discoveries and innovations needed for the required rapid mitigation and adaptation to climate change. As such, an event like today is a fantastic opportunity to discuss this approach, get more diverse feedback, and foster collaboration. And I'm very excited to chat with you later today.